overcome some of the challenges and still gain something in terms of the computational time. So there have been different approaches, and I'm only taking two out of the many here. So this is by no means an exhaustive list, but I'll talk about energy efficient path planning and optimal path for multiple tasks. And finally, we'll discuss a little bit about obstacle avoidance, which is what we do in our group, and we'll see a little bit about it. So when we talk about energy efficient path planning, the energy efficiency computation for a ship is really complex. It really depends on a whole number of factors. And in this particular study, they were looking only at two factors, which is the ship speed and the ice concentration. Assuming that I know how the ice concentration is around, I want to figure out what is the most optimal path I want to choose, whether I want to go with the shortest distance or do I want to go with one which saves me the least amount of fuel. And what you see in these two pictures here is the white. The red denotes the really strong ice concentration and the green is light ice concentration. And it's kind of very clearly seen that between the shortest distance and the least energy, you see that the least energy makes some turns around in the green region, trying to optimize on going through a low ice region so that it can improve fuel efficiency, even though its path is longer. Okay, so these are some areas. So particularly if I want to identify energy efficiency, that it's not very clear how it is directly related to my particulars. So that is where neural networks and deep learning really come into the picture, where you take in the real data from real ships and try to identify this relationship out of it. Obstacle avoidance, this is one which is close to my heart because we work on this day and night on our vehicles. The vehicle which you saw at the first slide, we employ these methodologies on it and we try to simulate them and we also try to do experiments on them. So what you see here are deep reinforcement learning agents, which means that these agents have no knowledge whatsoever of the model of your craft. Okay? And here we are considering a full-size container ship and in the simulations. And the idea is, at least on the picture on the left, you're starting off with a forward speed in the x direction and asking it to go to the green dot. And as it starts turning around, it encounters an obstacle which is really, really big. And the ship is now tasked with a local planner to avoid it and continue on its process. The deep reinforcement learning agents are quite successful in handling such tasks, and what we have found that they are very, very robust too, which means that even if I try to disturb the system with really strong winds, and this is still a simulation study, we have not been able to do experiments on that strong wind speeds, we need a hurricane to simulate that in the real world. Okay. So, but you can still see that it is able to follow the path even though I have strong, really, really strong disturbances, up to 6 times the ship's speed, and we are able to avoid them and continue on the path. The problem with these methods is definitely that the explainability comes into the picture. So the traditional control approaches can be mathematically proven, and you can tell that there are certain guarantees I can give. It will be stable in this region of operation. The problem with these methods, the reinforcement learning methods, is that I can't guarantee that. I don't know what the model has learned. That is a very good area of research which is going on, which is called explainable AI. And typically people are trying to understand how we can estimate how much the model has learned and augment it with what humans have learned so far. Okay, that brings me to the last part, the control. And in control, typically we have different types of control. And I know that since many of you are here from electronics engineering, might be aware about that. So we have point stabilization, where we want our vessel to reach a particular point and stay put. This is what we call as dynamic positioning. Or we may have a target tracking, where we want to track a target without having any knowledge of how the target is going to move. Then we have trajectory tracking and path following, where we want to track a particular path with and without time constraints. And finally, the later ones, the maneuvering and berthing, are the newer areas which are coming into the picture as we are moving towards autonomous vessels. You're seeing that in the maneuvering and berthing. Berthing specifically requires us to come and approach a berth at very low speeds. And when I reduce my speed, the vessel loses its maneuverability. The rudder is not as effective as I would have thought it to be, and that becomes a much bigger control problem, which is still unsolved as of now. So artificial intelligence can definitely help in those areas. Okay, and DL for control is something which we are very interested in my group too, and we typically test out these things in our lake, and that's what you see on the top there. It's a satellite view of our lake. It's about a 300 meters cross 100-meter lake in which we test out these vehicles. This is the first of the 3 vehicles we are building right now, and in the next phase we'll be seeing probably building a few more to come with, so that we can investigate cooperatively on the plot on the right, the plot on the left shows you how does an RL controller compare against a PD controller for the same part. And you do see that we do struggle with PD controllers sometimes, even though we have tried to tune it to the best of our abilities. So sometimes there is still some improvement in reinforcement learning agents where they are able to perform marginally better than traditional control algorithms. The picture on the very far right shows you one of our tests where we are trying to track a square waypoint path in our lake. This is a square of about 40 meters by 40 meters that our vehicle is tracking using RL-based controller. So going forward, so what are the challenges ahead and how can we address them going forward? So with respect to the navigation, the main challenges is the availability of labeled data set. We currently do not have very good labeled data set, and I would encourage my previous speaker to please participate in sharing some information with the academia in order to make that a possibility. So definitely we have excellent students who are looking into those areas which you. In addition, in terms of navigation, further things is detection in a cluttered environment, multi-ship detection, multi-scale ship detection, where I have a big ship and a small ship in the same picture. How do I detect them is still an open challenge, which definitely requires more thought process. Similarly, with respect to the guidance system, following of the COLREGs, which is the collision avoidance, the collision regulations set forth for the waterways. So just like you have rules for the road, you have rules for the waterways also, and how to ensure that a vehicle follows these waterways, the rules properly when it is an autonomous ship is still an open area of investigation. With respect to control, we have seen very few field experiments than we would like. Probably now that the sensors are more accessible and cheaper, we will probably see more number of students participate in this, and similarly industry participate in field experiments to take this control. So thank you very much. This has been a very exciting opportunity, and I'm very happy to take any questions.
That was a really nice presentation. I liked it, and I see considerable intersection between your area of work and ours. Few questions I have, because there, again, like I mentioned, there is intersection. So, the Mazda ASB that you have tested and the prototype that you have, what kind of turbulence level you have tested it on?
So we have in the lake, unfortunately, I don't have control on what is the but we have tested it on inside our wave basin with up to sea state 2.
Okay. That's pretty stable then.
Yes, it's pretty stable.
Okay. And another problem that we are facing, and on the orientation determination, are you working with a single sensor, or you are employing multiple sensors to figure out what kind of orientation does it have, like IMU in conjunction with few other sensors?
Right now, this one vehicle was using only the GPS along with the IMU.
Right.
And the GPS was not RPK in this sense, so we were seeing about a 3 meters is the accuracy range. So if I have a fixed position where the GPS sensor is located, it will arbitrarily give me somewhere within a 3 meter circle radius the position.
Right.
So I don't technically trust it too much. So when I tune my Kalman filter, I'm really worried about how much to place my trust on one sensor versus the other sensor.
Right. I see your point. We are facing a little more, some different kind of challenges because when it's underwater, we do not have GPS. So, yeah. But okay, I understand. Moving on to the third question. So, are you running the AI engine on board real time?
No. So what we do is we train the AI on a simulation model
Okay.
Offline. And once I have been training it for a good while and I see a good convergence on it,
Okay.
and I'm confident that it's not going to sink my ship, I take them and port them onto the model and let them run on it.
Understood. So, I'm assuming your system configuration, as far as computational power is concerned, is of moderate in nature, right?
Yes, so the vehicle which you saw there is only running Raspberry Pi and Arduino.
And it is not draining the battery and all.
No, so we have 4 lead acid batteries and we are seeing a good strong endurance of close to 3 hours.
Yes, yes. That answers all my questions. Thank you very much.
Thank you for your question. Any other questions?
Hi, this is Dr. Saliman Babu from Aligarh University. So, just want to know, you earlier asked what the difference between the two ships, one autonomous and the other was the traditional ship. So, that was the streamlined design. So, what is the advantage you are getting in streamlined designing and non-streamlined design?
You will be able to reduce the wind resistance. So what will happen is your windage area is reducing and it's more streamlined, meaning your drag is less.
Battery life and if you have any.
Oh, this won't be, that was more relevant for real ships. So here there would be, I think the equivalent comparison would be fuel consumption. So you can actually save a good amount of fuel. And studies have shown that it can be as high as about 3%, which is a big deal.
Thank you.
Any questions from the students? Here we have one.
Morning, sir. I'm Cadet Hadras from Ahmed University. Sir, this AI technology is only based on navigation or inside the ship? What about inside the ship?
Oh yes, what I have focused here is a very small gamut of the thing. Okay, so I have only looked at its application, or I have only shared its applications to guidance, navigation, and control. But you do see its application in many different places, whether it be in terms of fuel, and there is a lot going on in that direction too, especially with respect to route optimization. There is a whole new area in which there's a lot of progress going on. How do I optimize my route properly so that I can save more on the fuel? I fleetingly touched upon it, but I did not go too much into the detail of it.
Yes, sir. Thank you.
Thank you, sir, for your informative session on ASP developments, advancement with deep learning about the ASP systems, and the list of challenges you have put here ahead for the students to solve. Thank you, sir. And now I call upon Dr. R. Venkatesan, founder, chair, MPS, to facilitate Dr. Abhilakshya. keynote session is on AI on coastal science. Now I invite Ms. Preeti to introduce the keynote speaker, Dr. Shishir Kumar. Dr. Shishir Kumar Dash, currently working as scientist in National Center for Coastal Research, Ministry of Earth Science, Government of India. He completed his PhD in Image and Information Sciences from Graduate School of Science and Technology, Kaiba University, Japan. His achievements include ecosystem modeling for Chilika Lagoon, southwest coast of India, coastal vulnerability study for Tamil Nadu coast, Chennai flood warning system. He also awarded Certificate of Merit for his outstanding contribution in the field of ocean science in the year 2015. He published more than 20 papers in national and international referred journals, more than 15 publications in national and international proceedings. We are happy to welcome you, sir.
Good afternoon. Thank you organizers for inviting me and giving me the opportunity to talk on artificial intelligence. I'm basically a natural science student, but however, when 2 days back I got the invitation from the MTS that the organization told me that we give a lecture on artificial intelligence and on coastal science. And I understood that under Marine Technological Society, MTS is doing a wonderful job, particularly in this particular workshop on AI for the oceans. I think I will put my glimpse on the ocean and as well as coast. Mostly, when you talk about artificial intelligence, I think everybody might be knowing about the deep learning, machine learning, all these tools. But sometimes we understood that mostly it will be useful for object detection. But more than that, we can think what the human cannot think. Beyond that, artificial intelligence do. So I think this is the common things right now. I think everywhere it is there, whether you do the Google search or you can track real time how the Ola cab is coming to your house. So everywhere you know that deep learning and machine learning actually plays an important role, and you also know that there are a lot of data sets involved in that. So background, there are a lot of data sets are you have to compile and you to run, to put algorithms and everything. And so just I want to differentiate between the one slide where I want to tell you that what the difference between the artificial intelligence, machine learning and deep learning. When artificial intelligence where you can track or you can find an object, you can sense, reason or adapt. It is a program, correct? But however, for that to develop that, you need a lot of algorithms into that. So for the algorithm part, when it's coming, it will become called as machine learning, where different type of processes will be involved, whether it is complicated or sometimes it will be very easy to identify a object what a normal eye can see. However, what is not a normal eye cannot see, whether we can see that type of things, that also I will tell you in one of my examples, how machine learning can be used to identify certain things which human eyes cannot see that. And deep learning, which is also a part of machine learning, but it will take you little higher level, like identifying different type of neurons, and you can create a multi-layered neural network so that you can achieve what you want to be. Uh, but like my previous speakers, I just want to tell you that we work. I belongs to the National Center for Coastal Research. It is the attached office of Ministry of Earth Sciences where I am working as a scientist. We work mostly on the coastal applications, what coastal issues like pollution. We do long-term planning, we do long-term monitoring, prediction. So this artificial intelligence sometimes useful for us to identify different type of pollution. Like you might be thinking, what type of pollution? Yeah, one of the recently we are talking that on marine litter, that means marine plastics. Is it possible to identify different types of plastics you find in a beach through machine learning or artificial intelligence? I will tell you what activities we have done. The next one is that it is also as climate science and natural disaster prediction, and its recovery actually become more urgent and not. So that's why we are this type of artificial intelligence will tell you the exact truth. Like suppose a flood is happening, then how the flood, when a real-time flood is happening, mostly people do what? People do it. People do it. This much flood is happening, this street, this much happening, this street. From that, can you make any sort of modeling or prediction? Whether the water when once comes from one street to another street, which direction it moves, you don't know. At that time, you are not in a position to fly a drone. It is difficult for everybody to go and mitigate the flood. But however, how best you can predict that how flood is actually spreading in the city in real time. Looks a little bit unrealistic, but that type of things also can be done by using AI. I think that also I will show you some quick slides. Then there are the through machine learning, whether it is a drone or whether it is a satellite, using that, though there are a lot of machine learning tools are available right now, but there are a lot of IoT devices is also available right now. But the society wants to achieve better day by day. So why the society wants? Because they want to monitor accurately. They have to understand, they have to prevent damage and stresses about Earth and land, air and water. I think for that reason, this AI is always, most talked subject everywhere. In all the ministries now we are trying to do particularly what type of AIs we are actually doing in real time. And so that what will happen, this future of this AI, the future of this artificial intelligence will shape us to get a cleaner planet. I think these are my 4 slides which I just want to tell you about how you see, what are the things I want to talk. But basically what is happening at NCCR, I will come to directly that what we do. Wherever you see the red color, it is we do mostly object detection, right? There's previous professor also told about how you can track the things. So object detection mostly you do, but after finding object, we have to also see that how actually it is working or what is the future or how it is actually predicting certain things. Because wherever the sensors are there, in any we put sensors to measure a parameter. But after identifying the parameters, how we can predict? So most of the things, we use whatever open source is available right now, and mostly the object detection and using satellite image, we are also finding out that each object. Then as well as it is also helpful for analyzing or assessing the post-damage control, like mitigation problems. So that is also it will be helpful. It is also sometimes helpful to identify the number of objects, not like only identifying only one object. So you have to count the total number of objects. So everybody does, but ultimately, what is the accuracy? People will talk ultimately, what will be the accuracy? I think without much wasting time, I just want to show you my first image, which as a part of coastal vulnerability study of Tamil Nadu, when we started, we got a very high resolution drone data. This is almost 5 meters, and this is off Nagapattinam, where you can see the entire coastal areas. Particularly different when the cyclone approaches into the coast. What is happening? A lot of tree damages. Last time I think one cyclone came and it was having a massive destruction. So you may ask that why AI, how it is used actually. Suddenly the government asked that can you tell me how many coconut tree actually lost? Do you think it is possible to count the coconut tree through a satellite image or in a drone image? It is quite impossible. So we thought, how, because we know that earlier we were doing only the buildings where, damage will be happening, structures, coastal structures will be affecting. So that type of studies we do generally. But when they come to a question that how much area, crop damage assess can be done, that is true, because mostly that is, you could take the land use pattern, land cover pattern, then you can see the pre-disaster and post-disaster what is happening. So that type of things can be done. But can you really count the coconut trees? Quite impossible, right? Because the canopy is very long, and from a drone image if you take, it looks like a bush or what type of plant it is, then you cannot know that. So that's why that is a big challenge for all of us. But still, technology always with us. So we made the training data sets, and after that entire only one small stretch we tested, and we used algorithms like YOLO and SSD. Then we have processed the image in NovoFlow like applications and TensorFlow, all this, whatever is available, we try to find out, because our ultimate is to target. So this is my output image. Now you can see that I counted very nicely. That and everywhere I have given a number. I have to present a number of probability. Whatever I am telling, whether it is right or wrong. That means I need immediately validation. So validation has to be done immediately. So wherever there is a water bodies is there that you can see, because your eye can see. But again, counting again coconut. So almost if you see most of the places where there is interference between the land or a structure or a building to coconut tree. Like suppose one building is there and 5-6 coconut trees are there around it. So at that time where overlap is there we found almost probability 0.56, but otherwise we found almost 80%. Now you may ask me, sir, then how best you can, how much area you have told? Yes, we told 5 districts of Tamil Nadu. So 5 districts of Tamil Nadu, because drone image was with us, and immediately with a single click we can tell about the total approximately this many hectares of So this is the strength of the AI. Similar way, recently just we have done, I think we are now trying to know, trying to improve our quality, because when we talk about vulnerability of a particular structure or a particular building, again, it is very challenging. I will tell you why. A building, this particularly mini hall, it might be vulnerable sometimes when there are 10,000 people where they are in this building. But if 5 people are there in this building, it will be not vulnerable. Correct? But I will tell you, even 5 people, if they are in this building, it will be vulnerable. When? If I will bring 90 above people in this building, correct, rather than young generations. Because again, it is so vulnerably when we want to you want to estimate. So this type of things actually always comes to a challenge to it. So I think at that time, different type of algorithms, particularly deep learning techniques, are quite helpful. The next one I just want to tell you that it is very interesting. When 2015, I think many of you might be experienced about Chennai flood. So Chennai flood when happened, we did develop Chennai flood warning system. But over the time, we used to predict, we used to give the forecast to the state government, and it was quite useful. But later we came to know that, and subsequently, after 2018, actually this entire program was completed. But after that, to 2023, we experienced, I think, four monsoon season in the month of November to December. But the one thing I think every citizen in this city may be experiencing when the rain happens in the city, but with that 15 days you all will be panic, right? How I will go office, how I will, whether today heavy rain is there, means that the entire city will be, school will be switched off, called off. So, so 2-3 days, 2-3 particular occasions we last 3-4 years we have observed that the social media is very active. So what we do, we took all the Twitter handles on all the Facebook pages or different type of platforms, and we took the keyword of flood. When there is a, suppose cement cherry, how much flood is there, people will tweet. So we try to get, we did one algorithm particularly for, we developed one algorithm for that, to take particular 3 months tweet or immediately 3 hours tweet. 3 months to 3 hours. Why I am telling you? Because 3 months you see that sometimes what happens when a Twitter, when a person is putting an image, we have to know whether it is an image, real time image, or it is a large image. So the 3-hour image we took, and we see that actually we try to find out the authenticity of the image, whether it is right or wrong. Then after that we put an algorithm of machine learning that. I think I will show you that better. So there is a flowchart was there, we developed one flowchart for that, how data collection can be done, then data processing will be done. And everywhere annotation is very, very important. Then augmentation will be done. Then after that, we have to train the data. That is the most important part, because without training you cannot do the validity, because your comparison is will come last. Then after that we fine tune, and we will create the output model, and we will predict the output. That means a particular area, suppose 5 meter water depth of a photograph. You don't know what is the depth of that. One person will simply show a photograph from a rooftop or somewhere. But it is heavy rainfall is happening, and we know how much inundation will happen in that place. However, our basic objective is what? The flood is called in terms of depth. How much feet? Right? Any picture if you call, it is called, people will call the definition of flood always tells in terms of feet. So when a picture will be given to you and you don't know what is that depth, either one person has to go there and from that place if you cannot get that picture, you have to at least map the surrounding areas, how much it will protect it. So these are the very difficult situations you will face while predicting. So that type of things we try to do, and finally we test the thing. So just one or two pictures I don't want to show you how actually we predicted the flood depth. So these are the pictures we have taken. We know that one person is standing in the water, and he has approximately, you can tell what is the feet of that. Then after that, in the testing images we have taken how much, what are the real time images, that validation we take. And after that we try to identify, when we predicted that, how much actually it is going to be affected, because the rain is continuous. Now raining is happening, and it will, that rain will continue up to evening. Now though that there is a 1 feet water in the SRM, after evening, what will be the water you may not know. but the user has to, we have to tell that user that how much sexually the water has to be in the evening. If the same intensity rain will happen. So for that reason we predicted, it may increase 1 feet or 2 feet with a confidence level, and also and by considering also the severity of the climate. So all these three things we have taken into consideration and we predicted that. So this is the way we did. I think now this work is not completed, it is still going on because there are a lot of challenges still we face because when the real time is, when the rain is happening, nobody will go into the road. So you have to go into the road and you have to collect the data set. Then that data sets you have to fetch into the thing. Otherwise it is difficult. So these are the challenges still, but through our last 3 years we have collected almost 1800 points in the city. So these 1800 points give you the exactly how accurately you can predict the flood level. I think this is one example I want to tell you. The third one I just want to tell you that very interesting, I think the students will find encouraging about how actually marine nature. Though Dr. Somajulu told about very difficult about the tackling with satellite images. I do also agree with that. Satellite image, whether it is optical or remote sensing based or synthetic aperture radar, the resolution is always an important. Number two, in the optical again, one more problem is the cloud. So cloud is always a threat. So you cannot get the picture what you want whenever you want and the way you want. So sometimes if it is a dust, if it is even in a haze type of clouds also will be there, entire pixel will be black. Now when the pixel will be black, you cannot do because the relative transfer when how light actually transmits from the satellite to the earth and it again go back. So most of the things when you while processing it will be nullified and everything will be black. How at that time you need to fill that gap, and during that condition you have to identify different type of marine nature. It is almost challenging. So we used most of the time multispectral satellite images, synthetic aperture radar images. We also use different images from the shore or sea-based camera, or even sometimes phone camera also. Sonar data from submarines also used, and we use the deep learning technique particularly for identifying image segmentation and object detection. Because here, here the challenge is that a pet bottle, this level is there. If I remove this level, and similar way, if I make a glass bottle, you cannot differentiate. Right? One piece of plastic and one piece of glass, if it is fall on the road, you cannot distinguish. But so there is a big challenge that how you have to identify the marine plastics particularly. So for that, we developed one algorithm. I think that's only I wanted to show you. So we construct some different type of data sets. Then first we have to label it. What type, like normal segregation is happening in the different type of industries. So we have to find out different type of plastics or type of filters. We do two type of things. One is we do the scientific, completely optics related research, where we create all spectral libraries of each type of object. That is one. The second part is that by using AI. So after that, we have to label everybody, each and individual item. Then that we will transfer into algorithm, and training data sets will be there. Then after that we will do the validation. So for that one flowchart, just I want to explain you. So we got the input images, training data sets, and we have classified now suppose 6 varieties: plastic, paper, glass, metal, cloth, and other debris, biodegradable or something like that. So all this to be segregation has to be done. multi-class labeling has to be done, augmentation has to be done, transformation has to be done. Then after that, you can pass through different type of algorithms. Okay, so this with the particular architecture plan you have to do, because sometimes all the objects may not come. So some objects will filter there and some objects you will not get it. So after that, that's why we are choosing one by one. Then after that, it will be put it in the training model, and finally we can get the prediction. As I told you, the plastic is always a problem, always have a conflict with the glass. So where there is a severe conflict will come, we will put it as a, you will go into again, optically how, what is the spectral, what is the DN values of each object that we will find out. So that's why we differentiate that thing. And I just want to tell you that with that type of technology, 2022, 75 beaches in India at a time, we have collected the samples. Many places, so most of the places we have quantified physically, because that is object was there. But still, by using AI alone, the amount of debris we have quantified, which is very, very amazing. So we have collected almost 589 quintal of case, almost 5.8 tons of marine litter in the India on a single day of 3 hours, from 9 to 12. And then that we have state-wise we have done, which one is good. So when we started this work, then everybody appreciated that, it was a good work, though because most of the people in SRM was involved in that during that time. But our machine learning tools was quite helpful and collected enormous images. Now we are thinking how best we are going that, if somebody will take a photograph in a beach, then he has to tell whether the picture contains 70% plastic, 70% or 10% glass, 10% styrofoam. So like this, categorization has to be done. I think that is that for that purpose only we are now working onto that. How best, because it is not easy to do, because the picture, if I will take from the top, it will be different. If I take a picture from the left hand side with the angle, it will be different. So that type of things, I think we are having a good collaboration with the Japanese technology. So I think that subsequently we will try to get. Next, one interesting part I just want to tell you that apart from that, this is all object detection, whatever your eyes can see. But certain things if you don't see, as I told you that that there was a satellite image, when you see cloud is always a threat, and so whether when satellite is taking optical images, whether can I feel the clouds by using artificial intelligence? Yes, it is possible. Next question, I will ask that whether you can, suppose that the ocean color is blue, right? Mostly in the deep ocean color, but the coastal water is green. Why it is green? Because it contains pigment, no? And it contains chlorophyll. That means you can easy to estimate chlorophyll very easily. When chlorophyll you can estimate, is it possible to identify how many fishes are there? Can you count the number of fish? No. But yes, by using deep learning techniques you can do it. You can estimate even up to the primary production level. So what is happening during that time, you have to understand the system, how actually primary production takes. I think I will just one line only I will tell, one equation only I will tell, because I have not written here. I think everybody in your school test you might have read CO2 plus H2O is equal to C6H12 O6 plus O2, right? General equation of photosynthesis. Where in the arrow mark your below will be your heat will be there and top chlorophyll will be there, right? So that means what? Inorganic carbon in the left hand side, CO2 plus H2O with water, it will form as a glucose. and your right side C will be your organic carbon. Now, when a satellite image, if you take a chlorophyll image, you should know how much what is the chlorophyll in there, and there is a heat will be there. In ocean, what is the heat? It is the temperature. Correct. So you need chlorophyll, you need sea surface temperature. If you know these two parameters, can you estimate organic carbon? Yes, it is possible. Now, how you do? So that is the all about this paper where actually during my PhD I was doing for this primary productive estimation. So similar way the chlorophyll A purpose you need different type of functions like empirical orthogonal functions. You have there. So these two techniques where you people mostly use in data interpreting convolution autoencoder and as well as empirical orthogonal functions. So these techniques mostly useful where you can take the input data, then after that you can apply two type of things. Where again because there are two parameters is involved, chlorophyll and SST. So you have to take 2 into 2. That means first chlorophyll, then chlorophyll plus SST, then SST alone, then after that again chlorophyll plus SST. And that means each time you need to do at least two times. So one is chlorophyll, SST, chlorophyll, SST. That means 6 occasions you have to do. So particular area if it is dominated by the chlorophylls. So at that time you need to use all the 6. Otherwise in the ocean if you can use only 4, either temperature or one chlorophyll. So all this type of data if you take, then you can see that how your estimated chlorophyll and predicted chlorophyll comes. So then only, as the cloud is, I always tell you, is a major threat always. So this type of binnings or data binnings, whatever you do, then that if you apply, then you can get the realistic picture of how much plankton is available or how much primary production is happening, what condition it is happening. So up to this level, which your normal eye cannot visualize, that type of things can be. I think this is all about the applications of where we are also working. Now we are trying to develop in NCCR. We are also now working in a platform where you can one scale called Toralul scale, where by using deep learning techniques you have to identify that if your water is there, what type of turbid level it is. So that things we are working right now. I think this is all about my area. So we are now we are just heading in that neural network approach to estimate mostly ocean primary productivity. And this ocean primary productivity, if you estimate perfectly, then you can estimate how much carbon actually is contributed. So that's why this AI techniques will always helpful. It is also helpful to reconstruct the gaps. I told there are different types of gaps are there. So that type of gaps we can fill by using artificial neural network. Then there are a lot of prediction models study is involved already there. Now we are also doing. I think wherever we go, we tell that this neural network techniques by using predictive models to be used both open ocean and the coastal ocean. So mostly deep learning is nothing like input one, then system will take care and output can be done. That will be called as a black box. At least every level you have to know that why it is happening, how it is happening, why, then ultimately what type of product you are. If you understand that things scientifically, then I think you will be a very good contributor, particularly working on this AI. I think with this I conclude my talk. Thank you for the great opportunity. Any questions?
So I have a question that you said that we can use social media handles like pictures of the flood and to measure the depth of the flood, which we can. But is traffic cameras also being used, because
Yeah.
that way authentication and the calculation of that will be much easier.
Exactly.
That one. Because why these things came to our mind, actually this flood warning system was not developed for Chennai, we did for Bombay also. So Bombay when we did, we found that the same problem happened. The traffic is always, well, any picture may be wrong, but traffic is always right. Correct. So we have taken from there only we have got this idea, and traffic though we overlaid the picture, but sometimes there is a water is in the next street. Suppose one road is flooded on a particular small stretch, let be 10 meter or 20 meter. Entire traffic up to 1 kilometer it will be struck. But you cannot tell that how much water actually is inundating on the road. That's why this 1 kilometer stretch is actually low. So for that only we thought what to do. So you need a photograph during that time. Or somebody has to go there, at least put your feet and at least approximately one keyword I want. Whether it's approximately 1 or 2 meter, 2 feet. I cannot write there 6 feet, right? Because 6 feet, suddenly 6 feet water will not come there. So for that, little ground truthing was required. Of course, whenever in Chennai city, we immediately rush to the site and we took the picture from what you asked, from the traffic only, wherever, because traffic again, there are color codes are there, very dark to black color to, yellow color like that. So wherever there is a dark color there, we have tried to first we have went there and we at least some social media photograph can be posted, and based on that, we train our analysis.
So, like I'm talking about the pictures that traffic cameras collect. Because Chennai being a metropolitan city,
Huh.
we have cameras
Oh,
everywhere.
okay. That
So,
that
that may be
data, no,
calculation.
that data we did not get. But that data we did not. In Bombay, there was a lot of because this program was doing in Bombay. There were a lot of cameras were there from there we got. But in Chennai we did not get. Okay. Any other questions, Manoj? Thank you.
Thank you, sir, for your informative session about your research work and the model architecture, what you have given, and the knowledge you shared on marine litter recognition and all. Thank you, sir. Now I call upon Dr. R. Venkateshan, founder and chair MTS, to facilitate Dr. Shri Sama. Now it's time for the lunch break. We will resume by 2 p.m. here.